The logistic equation, you're going to need to know both of these equations, the dy dt one, which is a differential, and then the y equals one, which is the solution, the general solution. Okay, I made a pretty cool PowerPoint on logistic growth, and I want to show it to you real quickly. It should help you with the formulas, at least understanding where they come from. All right, most of the problems will be given as a diffie-q. Instead of dy dx, it's dy dt. So this is the differential form of the logistic growth equation. And as you can see, here's the basic shape of the curve. You start out slowly. The curve rises real slowly. It picks up steam in the middle, and then it kind of tapers off again at the end. Eventually, when things start to level out, there's a limit that you sort of start to approach. It's really a horizontal asymptote, and usually most textbooks will call it L. L for limit, I suppose. And in biology, it's called the carrying capacity. A lot of times, things like rabbits, let's say, for example, you have their natural habitat. Rabbits will start out growing, pretty slowly, and then it really picks up steam as more rabbits have baby rabbits. But eventually, their predators get to them, or the habitat can only hold so many. There's not food, and so it starts to level out. So that's logistic growth. Restaurants grow the same way. You think of Subway restaurants. I use that a lot in my example. The first time I ever saw a Subway, I was in high school, and they usually just had them in college towns. And eventually, more and more Subways started to open. Now it's been going crazy recently. Every Walmart has a Subway, a lot of gas stations, man. But eventually, the number of Subways are going to level out. You can't have 20 Subways in Beechwood. It's just not going to support it. So again, logistic growth is very common. Now here's the bad news. If I wanted to solve this diffie-q, this dy dt, and just get it to be y equals, it's going to come out to that. The equations don't really look alike. The L in each case is the carrying capacity. T is time. But man, it's really messed up. You have to figure out what the C's and the K's are, and it's hard. I would recommend just simply memorizing each equation. If you don't memorize both equations, the second one, actually, I kind of get helped out because of my last name. It's L-U-C-E. I can almost see my name in that, except the U is a 1, but for what it's worth. But still, you have to figure out a way. If you don't want to memorize it, you can always figure it out using these steps. All right, here we go. First thing you're going to do is separate variables. All the y's and dy's on one side, all the t's and dt's on the other side. So I'll kick the dt to the right. I have to divide both sides by y. But since a couple different things have y's in them, I just divided by a whole bunch of stuff. The only thing left on the right-hand side along with the dt was the k, which is a constant, by the way. All right, if you integrate both sides, here's what's going to happen. The right-hand side will be super easy. Remember, k is a number, so if k was 2, it would be 2t. Or if k was 10, it would be 10t. So it's going to be kt plus c. The left-hand side, though, requires partial fractions to get the left-hand side. Remember, the right side is kt plus c. We'll put that on the back burner and bring it back in a moment. All right, left-hand side, here we go. I'll split it into partial fractions. It's already factored. I need to get the common denominator, so the first parentheses will get multiplied by 1 minus y over L, top and bottom. The second one with a b will get multiplied by y, top and bottom. That'll be equal to 1 because there's a 1 in the original, where that dy is kind of off to the side. So I need to solve that equation. I'm going to start out by making y 0. If I make y 0, the b's disappear. In fact, I'll just have 1a equals 1. And so a will be 1. All right, so that's cool. So a is 1. Now, if I want to figure out what b is, I need to make y equal to L. Because if y is L, you can see the first parentheses will be 1 minus L over L, 1 minus 1. That'll kill the a off because that'll be 0. You'll have BL equals 1, so b will be 1 over L. Ugh. Okay, so once again, a is 1, b is 1 over L. So 1 over L. Let me bounce those in here real fast. Okay, let's give ourselves a little bit more room. And before I integrate, that right one's just looking terrible. I hate the fraction within a fraction. Let's multiply numerator and denominator both by L. That'll make things a little nicer. Yeah, there we go. All right, integration. Integral of 1 over y dy, that's just natural log of y. And the second one has a quick u sub. The u actually is going to require a -1, so you're going to have to pull a negative out front, but no big deal. And remember that we just used partial fractions to get the left-hand side. The right-hand side was kt plus c. All right, we've run out of room, so let's give ourselves a little bit more space. And in doing so, I'm going to combine the two natural logs using algebra 2. Remember, a fraction means that you can stack them up. I should say subtraction means you can stack them up. And so I did. And now I exponentiated. I took an e to both sides. E to the natural log, of course, canceled. E to the kt plus c is on the right-hand side. Next, I took the reciprocal of both sides. I just flipped them both upside down. Totally legit. When you flip something with an exponent upside down, the exponent turns negative. So the kt plus c, I just changed both signs. I usually don't like changing the sign on the plus c, but what the heck. It's a mystery number. I realize it. Okay, let's, again, more room. All right, I pulled a little bit of algebra 1. It's going to be e to the negative kt times e to the negative c. But again, e to the negative c is a mystery number, so it's just going to be c. I stuck it in front. Now on the left-hand side, I split the fractions. So I have L over y minus y over y, which of course is 1. I added 1 to both sides. Again, running out of room, so we'll go back up top again. Again, I reciprocated both sides, just flipped both sides upside down, which is fine to do. It's really just cross multiplication, except you save a couple steps. Speaking of cross multiplication, that's exactly what I did next. And finally, if you divide both sides by the parentheses, you get that loose formula from the first page, except it's a 1, not a u. Oh my gosh. If you don't want to do those, 15, 20 steps every single problem, you'll take my advice and you'll memorize what's in that red oval there. Really, you ought to have both of them memorized. That's the expectation. Okay? But I didn't want you thinking that the formula was magic. It does come from somewhere. It comes from a lot of algebra, mixed with partial fractions from chapter 8. Okay. Here in my example number 1, I'm asking you guys to find the logistic equation that satisfies the initial condition 0, 14. I gave you a differential equation, dy dt, and we want to get it just back to y equals. The first couple things we need to figure out are what's k and what's L. I think you can see that k is right here. K is the 0.75, and the L in this case is going to be the 70. That's L right there. And we have everything else that we need. We're not doing the 20-step derivation. I have the other formula memorized, and here it is. Man, talk about a time saver. Now, the 0, 14 needs to go in. Keep in mind that the 0 is time. It's sort of like the x except it's t. And the 14 is the y. So we want to plug those items in. And what will happen is this is just going to become c times e to the 0, which is c times 1, which is just c. Since 14 is 70 divided by 5, I know that the 1 plus c in the denominator needs to be 5. So therefore, of course, c is going to be 4. Taking the 4 and plugging it back in, gives us our final equation. All right, here's example number 2 I made up. It says the State Game Commission releases 40 elk into a game refuge. After 5 years, these 40 elk have increased their population to 104. Commission believes that you're not going to be able to have any more than 4,000 elk in this game area. And we have a growth rate given to you. And the growth rate is modeled by a Diffie-Q that I wrote down there. That's that dp/dt. That's the derivative of population with respect to time, so it's a rate. And t is in years. Okay, part A. Write a model for the elk population in terms of t. We'll do that first. And that's simply going with p equals and transferring a Diffie-Q into a regular logistic equation. I know that this 4,000 is the carrying capacity. You know, it says the environment can support no more than 4,000 elk. So that's the L. And I know that the L is going to go up top in the numerator. So that's 4,000. I know that it's 1 plus c e to the negative kt power, because I memorized that. I don't want to do that 20-step PowerPoint every time I solve a problem about elk. And then I can plug some numbers in. Really, I have 2 pieces of information. I know that when time was 0, the elk population was 40. In fact, I'm going to label this T, comma, population, T, comma, P. I also know that when time was 5 years, the elk population was up to 104. So you can almost consider those to be points on this graph, and I can try them in. Well, obviously, I'm going to try the 0, 40 in first, because I love having time be 0. It makes my life a lot easier. This P will become a 40 temporarily. Also, I love the fact that it's 40 because we have 4,000 divided by something is 40. And obviously the something part would have to be 100. So let me do that real quickly here. 1 plus c e to the 0, which I'm not even going to write because that's 1, is equal to 100. So I found c. C is 99. And that'll be extremely helpful. All right, I'm going to go ahead and at this point, I think I'm going to go to a new sheet of paper. I'm going to rewrite this red equation without all the blue over it. And when you see me rewrite it, you'll see that I have P equals 4,000 over 1 plus 99 e to the negative kt. Okay, here goes. All right, there's the rewrite. I've got some working space. I've already used the point 040, but now I can use the point 5, comma 104. That'll get me the only other thing that I'm missing, which in this case is the k. So in this goes, this is not going to be nearly as slick as the 040 was, but that's okay. I don't expect elk to know enough calculus to give us whole numbers in our work, so it's just going to be what it is. All right, 104 is the P. 5 is the T. At this point, this just becomes algebra 2. Now, if I want to find the stuff in this cloud right here, I can just use what we call in the younger grades a turnaround fact of division. If 104 is 4,000 divided by cloud, then 4,000 divided by 104 is cloud. Sorry, I keep saying cloud, but The stuff in the cloud is going to be 4,000 divided by 104. And 4,000 divided by 104 is 38.4615. All right, that's equal to the 1 plus 99 e to the negative 5k that I'm about to copy down. I'll subtract 1 from both sides. And I'll divide by 99 to give me e to the negative 5k. And then, of course, from algebra, we just natural log both sides. That allows the power law to occur. Negative 5k comes down. Of course, natural log of e is going to be 1. I take the natural log of the left-hand side, divide that by negative 5. That'll give me the k that I need. When I do that, I get k equals 0.194. That k value will go back up into this equation, and that'll be the equation and the answer for part A. All right, and finally, we have the answer to part A. There's the equation for elk population. The nice thing is, part B, it says estimate the elk population after 15 years. Well, heck, all we have to do is just plug a 15 into the t and just see what we have. This can be done also just by graphing this and just looking at the table, t equals 15, and just see what the p, or the y side of the table says. And when you do that, you're going to find that it's 628.538. We're going to round that to the nearest elk. I'm going to round that up to 629 elk. I know some people are going to be like, but 0.538 of an elk won't live, so you should round it down. Yeah, whatever. I'm just going to say round to the nearest animal on the test. So maybe I'll make it something that rounds down anyway. Who knows? Finally, part C. Find the limit of the model as t approaches infinity. I could have done this before I did anything else. This is the easiest answer on the page. The answer is the carrying capacity. If time goes on forever, the elk are going to hover right around that 4,000 limit. They won't be able to grow anymore. The logistic curve will approach that asymptote, and that's it.
Last but not least, example number 3. You've got this differential equation, dp dt, measuring a population, p for population, and it's in the form of a differential equation, so we have to sort of figure out what's what. Typically, you've got dy dt. This is dp dt, which is fine. And that's equal to kt, because it says it's logistic. And then inside the parentheses, 1 over, normally it's y, here it's p, over L. And L is the carrying capacity. Speaking of carrying capacity, you know what that really means. Think about this. Here's the x-axis, y-axis. The carrying capacity is right here. This is the L. And of course, we know that the x-axis also serves as a horizontal asymptote. Any logistic curve is going to come like this. It's going to come upward, start growing very steeply, and then sort of wimp out again and hug that L, or that carrying capacity. So here they say, hey, p of 0 is 6. So we're crossing the y-axis at the point 0, 6. What's the limit of p of t as t approaches infinity? So as time approaches infinity, remember in science class that the x-axis is really the time axis. So let me change variables on us. There we go. So as time approaches infinity, we're going to be heading to the right, forever. But the limit is simply going to be the carrying capacity, which is the L, which is this 76 right here. So the answer to the first question is 76. What if you start at the point 0.85 instead of 0.6? What if it's up a little higher? Well, it doesn't matter. The answer is still going to be 76. I guess actually if you were up here, you would have to come down approaching the axis. Your logistic would just kind of go backwards like that. In any case, both answers are 76, which is the carrying capacity. Finally, our last question says, for what value of p is the population growing the fastest? Remember, p is like y, so this is the p-axis for population. Well, the population is growing the fastest right here at the point of inflection, because that's where the slope is the steepest. You know, when you're over here at this green point, the slope is relatively flat. Even right here on the y-axis or the p-axis, it's flat. But right here, that's some serious growth, and then the growth starts to tail off again until it's not growing very fast at all. It's pretty much not growing. So the fastest growth is at the point of inflection. How high up is the point of inflection? It's exactly halfway between the x-axis, t-axis, and L. It's half of 76, which happens to be 38. So that last answer is 38. And this is true regardless of what the equation is. It doesn't matter if it's got a 3/4 p in front or a 76 or different numbers in both places. It's still going to be halfway up. And that should make sense in real life. If you think about it, let's say that you have a different example over here. Let's say you have 100 people. And there's a virus going around. Imagine that. And 3 people start with it. And it starts to spread faster, 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 faster. But then the spread slows down because, let's face it, once you have it, you know? And so all 100 people become infected. When's it moving the fastest or spreading the fastest? When 50 people have it. And again, that should make at least a little bit of common sense, because if 50 people have it, that's plenty of infected people who were able to spread it, and there's still plenty of victims who are able to catch it, right? If only 3 people have it, it's not going to spread real fast. And if 99 or 100 people have it, it's not going to spread very fast, because who are you going to give it to? So that's why the point of inflection in a logistic equation always occurs halfway up. So that's an easy answer, 38. And we're done with logistics. Good job, everybody. See you next time.